Hello everyone, I'm Pierre Mahé and I'm going to present my work on Ambisonic Coding with spatial image correction. This work is done jointly with Stéphane Rago, Sylvain Marchand and Jérôme Daniel. So let's begin with a little bit of context and motivations. Currently, the telephonic codecs are mostly still mono. However, more and more devices support spatial audio with dedicated devices but also with smartphones equipped with more than one microphone. Besides, new spatial audio applications emerge such as virtual or extended reality. Because building a whole codec is very complex and time-consuming, our approach is to reuse existing core codecs. Briefly, some examples of spatial audio usage. Call with 3D ambient sharing, immersive content broadcasting, spatial audio conferencing, where each participant is spatialized in the room to improve intelligibility. There are different ways to represent spatial audio scenes. Ambisonic have become an attractive format due to its flexibility in terms of recording and restitution setup. Ambisonic is a sound field decomposition into a spherical harmonics basis. The signals project on one dimension. It's called Ambisonic component or just component for short. This format was invented by Gerson for first-order ambisonics or FOA and later extended by Daniel for high-order ambisonics or HOA. For a given order n, there are n plus 1 squared components. The figure on the right shows the three first orders. Let's see a quick example to illustrate how a monosource is spatialized. The source S is projected into the ambisonic domain by an encoding vector. The direction sigma and phi determines the values of the vector. The dot product creates BT, the signals for each component. We have just seen how it's ambisonic. Now, let's see how it's traditionally encoded. The baseline approach is called multimono. Each component is coded and decoded independently by a core codec. The bitrate distribution between components is fixed and usually uniformly distributed. The figure shows the illustration of multimono approach. The alterated signal is not with a tilde. This approach has the advantage to being simple. For high bit rates, it works fine. But when the available bitrate is limited, strong artifacts and spatial distortion occurred, such as diffuse noise and phantom source. Those artifacts are visible on a spatial power map. It's particularly visible for a broadband source. The figure shows a screenshot for a pink nose rotating around the listener. On the left, the power map of the original. On the right, the power map of the coded signals. The phantom sources and the diffuse noise are easily visible. Those observations create an idea on our minds. If the decoder knew the original power map, it could correct the spatial artifacts. From this idea, we'll propose a new post-processing method. Our approach is based on the computation of power map for the original and coded signals. From those, a transformation or correction matrix is derived. This matrix increases or decreases the gain in some spatial direction to fit the original power map. First step of our approach, the power map computation. The simplest way to compute a power map is to correct the set of points which discretize the sphere. For each point, a weight vectors dE is computed to create beamforming. With this beamforming, the signal coming from this direction is extracted. Then the power is computed for all the points. By rewriting equation, the power in all directions can be computed directly for the covariance matrix of the ambisonic signals. The covariance matrix is not C. The interesting thing is that a small symmetric matrix is enough to compute all points' power. For example, in FOA, only 10 different values represent power in all directions. the second step of our approach is to find the transformation matrix to correct the power map. The problem can be formulated as follows. For any direction, the corrected covariance matrix has to be the same as the original covariance matrix. For that, we need to find a transformation matrix T. With Cholesky factorization helps, it's possible to decompose both covariance matrices in two L matrices. Because L matrices are triangular, T is triangular too. Only with the 10 values of the T matrix, it's enough to correct the power map. This is the whole codec. The ambisonic signals goes into the encoder. After a high-pass filtering, the signal is compressed by the core encoder. Then it's decompressed by a core decoder at the coder side. In the power map module, both signals, the original and decoded, are divided into subbands. For each, covariance matrices are computed. After that, using Cholesky decomposition, the T matrices are calculated, quantized, and sent to the decoder. In the decoder side, the T matrices are unquantized and applied directly to the decoded signal. The figure shows the three power maps: the original signal, the decoded, and the post-processing one. If you look carefully, in the post-processing power map, the source has a little tail. It's because in the original signals, the source rotating around the listener, and the post-processing adds a little space lag. In other terms, the source position is about 5 or 10 milliseconds late. To evaluate our method performance, a subjective test was conducted. The test was a ref-A/B test. The subject has an explicit reference and two other stimuli, A and B. He has to compare those two conditions. The figure shows the test interface. The two conditions are multimono with and without post-processing. Two tests was conducted, one with EVS core codec and one with Opus, each with two subject panels and two different bit rates. The results showed, on average, that our post-processing improved audio quality. Let's take a closer look of the result. How to read this figure? This figure shows the score with the confidence intervals for 10 critical tested items. The horizontal axis is the different audio items. The vertical axis is the CMOS score, a subjective score of overall quality in terms of frequency and spatial. +3 score means the post-processed item is much better than the multimono one. In other terms, the quality is improved by post-processing. -3 score means the multimono items is much better than the post-processed one. The quality is degraded by post-processing. 0 score means the two items' quality is similar. On the figure, the test results for EVS are in blue, and the results for Opus are in red. Except for one item, the results are highly correlated. On average, the results showed that our post-processing improves audio quality. However, for 4 items, the quality is not improved or degraded by post-processing. Those items are a man reading an extract of Le Petit Prince at the fixed position in a reverberant room, theater, a play with 3 moving talkers in the auditorium, orchestra, an orchestra playing in the concert hall, applause at the end of the concert, the microphone was placed in the middle of the crowd. The common characteristic of those items is strong reverberation or a multitude of directions of arrival in each 20 millisecond frame. This characteristic will make those kind of items difficult to correct with post-processing. The degradation may also be explained by the reduced bit allocation to the core codec when post-processing is used, especially for the applause item, which is complex to code. An ANOVA analysis shows that the results are similar for both bit rates and both subject panels. To conclude, we have presented our post-processing for multimono coding. This method has aimed to avoid spatial artifacts and distortions. The post-processing improves audio quality for various core codecs in low and medium range bit rates. Thanks for watching my presentation on Ambisonic Coding with spatial image correction. If you have any question, please do not hesitate to contact me.